Let me continue our discussion on lateral torsional buckling. In this video, we will continue to have one example on lateral torsional buckling of a beam. A 533-165-66 kg per meter UB section in steel S275 steel grade, span 7 meter, supported by parallel columns in simply supported at A and G. A point load is transferred from a column at B of 150 kN. Each secondary beam attached at B and C transfer load of 100 kN. The beam is laterally restrained at both ends and at B and at C. Determine whether the beam has adequate buckling design resistance to bending moment. So on your left, you can see a beam attached at parallel column at A and at G. On the beam at B and at C, secondary beams are attached, and at B there is an intermediate column attached. So segment AB is 1500 mm, BC 1500 mm, and CD 4000 mm. So at both ends, the beam is supported, and also at B and at C. So we have unrestrained segment, 3 unrestrained segments here, AB, BC, and CD. So from top view, the possible lateral torsional buckling shape of the beam is shown here. The detail at B is also represented here. So these two secondary beams are attached on the web of the main beam, and then the intermediate column is also attached on top flanks. So this arrangement is a stabilized arrangement, so there are no any additional modified factor introduced later on in determining the elastic critical buckling strength of the beam. So from this example, we will highlight the important information. First, the size of the beam given here, and then the steel grade also given here. Its span 7 meter, and other information here that the beam is laterally restrained only at specific point at both ends, at B and at C. The information that we need to determine here is the end product need to be determined here is the buckling design resistant to bending moment. So what we need to do, first we extract all the information required from the standard section table of dimension and standard section table of properties of the beam, the main beam. Five three three 165 66 kilogram per meter UB section, and then it is S275 steel grade. And then the information that we can extract from here, we continue. Okay, first of all, we extract the information on the section properties and dimension for the series. So the H five to 4 7 millimeter, the breadth 165.1 millimeter, and thickness of the flange is equal to 11.4 millimeter. And then the design parameters that we can extract from clause 3.2.6 Euro Code 3.11 is the E is equal to 210 gigapascal, and the Young modulus and the shear modulus 81 gigapascal. Then the section properties, Iz equal to 859 centimeter of 4 plus the modulus about y-axis 1561 cube centimeter, and the warping constant IW, warping constant equal to 0.566 decimeter over 6, and then torsion constant 32 centimeter power 4. Okay, then for the unrestrained segment, LAB 1500 millimeter, LBC 1500 millimeter as well, and then LCD is 4000 millimeter. So then which one that we have to calculate? You just need to be remember that the longer the unrestrained segment, the lower the value of elastic critical buckling strength. So then we can determine this one as the L effective, or the unrestrained segment that determine the limit of the bending or buckling design resistance to bending moment. But before that, we have to calculate the determine the bending moment diagram. So in this case, we have point load here and point load here, P1 and P2. And then we have secondary beam at this point, and at this point, A, B, C, and D. So the bending moment diagram shape will be at this. That's M1, M2. Okay. So then the value of C1 equal to 1.77 at AB and at CD. And then along BC, the C1 is determined by the value of C, where C is the M1 over M2. And then C1 can be determined by using this expression. (1.88 minus 1.42 psi plus 0.52 squared. Okay, the first step is to do loading analysis. So let me continue. After we do loading analysis, so we have this value for bending moment at P and C. So then we can determine the value of C1 for the trapezium shape of bending moment diagram. So step number two here, we determine the unrestrained segment L, which is taken for from the longer segment only, 4 meter, 4,000 millimeter. Then step number 3, we determine the MCR. Basically, we determine the C1. The C1, a modified factor C1. So we take 1.77 for the for segment CD, the longer segment. So the longer the segment, unrestrained segment, so the lower the value of MCR. So the purpose we were doing the determining the C1 is to basically to also to determine whether it is the longer segment, unrestrained segment, play a big role to limit the design resistance of the beam or buckling due to bending moment. So after we do calculation for the trapezium shape of bending moment, the value is only the value of C1 is 1.03. Then it is considered not significant because the span or the unrestrained segment at the trapezium shape of the bending moment is only 1,500 millimeter. So that's why we take the longest segment here, segment CD. Then step number 4, we determine or calculate the MCR. MCR is the elastic critical buckling strength. So we write the expression MCR is equal to C1 times pi squared pi z over L squared times the IW over IZ plus L squared C modulus times torsion constant over pi squared Young modulus times second moment area over Z axis. This it is square root. So So then we fit into this expression all the information that we have. C1 is 1.77, and then phi squared AI is 210 times 10 power 3 times 859 10 power 4 over the 4000 times 0.566 times 10 power 12 for the warping constant over the second Roman area plus the unrestrained segment times the second shear modulus times the torsion constant 32 10 power 4 over the squared times the Young modulus 10 power 3 times 859 times 10 power 4. Then it is in the square root. So we got 588 times 10 power 6 Newton millimeter, and so it is 588 kilonewton meter. Next we calculate the non-dimension slenderness. Step number 5. Calculate the non-dimension slenderness. So it is square root of Fy modulus plastic about y-axis over MCR. So the thickness of the flanks where the buckling is occurred subject to compression is equal to 11.4 millimeter. And then based on the EN 10025 part 2 table 7, so this thickness is less than 16 millimeter, so then Fy is equal to steel grade S275, Fy equal to 275 megapascal. So then we can calculate the lambda LT bar is equal to square root of 275 times modulus plastic 1561 10 power 3 over the MCR 588 times 10 power 6 equal to 0.854. Number 6, we calculate and determine the buckling curve. Buckling curve based on value of his OB and refer to table 6.5 Eurocode 3 part 11. So his OB five to 4.7 millimeter over 165.1 is 3.18, and then it is bigger than 2. So from table 6.5 Eurocode 3 part 11, the buckling curve is buckling curve. So we will stop for a while. We continue. The buckling curve for his OB bigger than 2, refer to table 6.5 Eurocode 3 part 11 is buckling curve C. And then number 7, determine the imperfection factor alpha LT from table 6.3 Eurocode 3 part 11. For buckling curve C, the alpha LT is equal to 0.9. Number 8, calculate the buckling parameter. PLT, buckling parameter, where the PLT is equal to 0.5 bracket 1 plus alpha LT bracket the LT bar minus lambda LT bar naught plus theta LT bar square. So the recommended value for alpha lambda LT north bar is equal to 0.4, and then the beta is equal to 0.75. So by substituting all the information into this expression, so we can easily calculate the value of PLT. Zero point 49 854 minus 0.4 plus 0.75 times 0.854 squared. So it's 0.81. Step number 9. Calculate the reduction factor CLT. CLT is calculated by using this expression. There's 1 over PLT plus the square root PLT squared minus beta times lambda LT bar squared, and the value should less than 1.0. 1 over PLT 0.811 plus square root of 0.811 squared minus 0.75 times 0.854 squared. Let me calculate this one first. 1 divided by bracket 0.811 plus square root of 0.811 squared minus 0.75 times 0.854 squared. Here's the bracket, close the bracket. So it is 0.874, and it is less than equal to 1.0. But then step number 9 and number 10, since the value of C1 is not equal to 1.0, so we have to calculate the modified factor f. Value of f is also not equal to 1.0, so f is equal to this expression 1 minus 0.5 bracket 1 minus 1 over square root C1 times 1 minus 2 open bracket lambda LT bar minus 0.8 squared so let me calculate this one. Is 1 minus 0.5 in bracket 1 minus 1 over square root 1.77 times 1 minus 2 bracket open bracket lambda bar is 0.854 minus 0.8 in bracket. Let me calculate this. 1 minus 0.5 times open bracket 1 minus bracket 1 over square root 1.77 plus bracket for that one times open bracket 1 minus 2 in bracket times 0.854 minus 0.8 square in bracket close the bracket 0.929. So then number 11, calculate the modified radius factor, which is calculated from the CLT radius factor over the modified factor F. So CLT mod is equal to 8.74. Allah, sorry, 0.874 over 0.929. 0.874 divided by 0.929. 0.941, so it is also less than 1.4. So the calculation is okay, correct. And then Number 12. We calculate the MBRD, buckling design resistant to bending moment. So MBRD is equal to CLT mode, the modified reduction factor, times nominal yield strength times the plastic modulus for y-axis over gamma m1. CLT mode is 0.941 times 275 times, what is the modulus plastic that we have? Modulus plastic that we have here is 1561. 1561 times 10 power 3 over 1.0. So we have here 0.941 times 275 times 1561 times 10 power 3 is equal to 403.95 kilonewton meter. So number 13, to check whether the beam has adequate buckling design resistant to bending moment, we verify the MED over MBRD should less than or equal to 1.0. So in this case, the MED that we have is 640.24, 640. Over the 403 is bigger than 1, so the result is the beam has no adequate buckling design resistant to bending moment.